I'm really thrilled to be here to present to you Evaristo Villaseco Arribas for his doctoral defense, doctoral thesis defense. Evaristo was born in the Canary Islands and grew up there and in Madrid and Salamanca, which is where he did his undergraduate degree. He then did his master's in theoretical chemistry in Madrid and explored materials engineering at NJIT before joining my group in fall of 2020, right?
Yes.
Yeah. And since then he has been, for the last 4 to 4.5 years, he's been working on the development of accurate and practical methods to describe coupled electron-nuclear dynamics, as he will tell you about today, in particular under photoexcitation. Evaristo has published 8 papers. He's presented his work at national and international conferences. He won a Chateaubriand Fellowship to study under Professor Federica Agostini for 6 months in Paris, and he won a Dean's Dissertation Fellowship. Before I turn it over to him, let me introduce you the committee. We have Federica Agostini from Paris-Saclay. We have Professor Farnaz Shakib from NJIT, and our own Professor Michele Pavanello. And I just make one point here. Please save most questions to the end, except if you have an urgent question that needs a clarification or some such on a slide, please feel free to raise your hand. Okay, everybody's.
Thank you, Nipa, for the kind introduction. And hello, everyone, and thank you for being here today. It is my pleasure to present my PhD thesis, exact factorization-based mixed quantum classical dynamics. And this work could not have been possible without the guidance of Professor Nipa Maitra. So to begin, I would like to provide some context on the timescales that we're going to consider in this thesis. In this picture, I'm showing relevant timescales for different processes. For example, the human eye can see things that occur between a second and a millisecond. Modern camera shutter speeds can take pictures from things that range from a millisecond to microseconds, and modern electronics operate up to nanosecond timescales. The folding of the protein structure occurs up to picosecond timescales, and the motion of nuclei inside the molecules occur in femtosecond timescales, and the motion of electrons in attosecond timescales. So just to give you an idea of what an attosecond is, an attosecond is to a second what a second is to approximately 31 billion years. So these processes are extremely fast, and quark-gluon interactions in the atomic nuclei push even further, up to 10 to the minus 24 seconds. So in this thesis, we're going to focus on this range, in this temporal range. And ultra-fast molecular processes that occur here are quite ubiquitous and present in a lot of light-driven phenomena. And some examples of these are the photoradiation damage in DNA under UV light, the charge transfer in solar cell materials, light vision, and the molecular formation and fragmentation in the interstellar clouds. So a key for these processes to occur is the coupling between the electronic and the nuclear motions. So when these systems interact with light of the proper frequency, the electrons get excited, and this electron excitation couples to the nuclear dynamics, triggering an ultra-fast process that drives these processes, and that's what we call nonadiabatic effects. So now I want to give a brief historical overview of key achievements in nonadiabatic dynamics that formed the foundation for my research. So in the 1926, Erwin Schrödinger proposed the time-dependent Schrödinger equation that allowed to describe the time evolution of a molecular system. Soon after, in 1927, Max Born and Robert Oppenheimer provided the basis for the separation of electronic and nuclear motions, which allowed to describe molecular dynamics under a diabatic condition. In the 1932, Landau, Jenner, Stuckelberg, and London proposed the first theories of non-adiabatic transition. But it was in 1954 when Max Born and Kuhn extended the Born-Oppenheimer framework to include multiple electronic states and couple among those states that form the theoretical basis to describe photochemistry. In the 1970s, John Talley proposed perhaps the most mainstream method for non-adiabatic dynamics, trajectory surface hopping. In the 1981, Ahmed Sewai synthesized the first femtosecond laser pulse in the laboratory, and this allowed to probe nuclear motion inside molecules. He later got the Nobel Prize in Physics in the 99, I believe. In 2001, Krauss, Agostini, and Lullier synthesized the first attosecond laser pulse that allowed to probe electronic dynamics and later control it. They got the Nobel Prize in Physics last year. And in 2010, Hardy Gross proposed, and co-workers proposed the exact factorization approach, building in early work by Hunter, that we are going to discuss a lot of time today. And actually, I got inspired by Professor Farnaz Shakib's talk at Rutgers 2 weeks ago, and I wanted to see whether or not I'm academically related to these people. So I decided to look up my academic tree, and I was quite pleased to know that 5 generations back, I'm related to some of these people, such as Rödinger or Oppenheimer. So this is what's on the agenda for today. First, I'm going to start with a theoretical description of photochemical dynamics in the usual Born-1 picture and in the exact factorization approach. I will then discuss mixed quantum classical methods for nonadiabatic dynamics, comparing traditional schemes with methods based on the exact factorization. After that, I will show some results in 2 specific areas: energy conservation in mixed quantum classical methods and the description of electronic coherences in molecules. And finally, I'll provide a brief summary and outlook for future research avenues. So let's first start on how to theoretically describe these couple electronuclear processes. So we are concerned with solving this apparently simple-looking equation, which is the time-dependent Rödinger equation, in the non-relativistic limit. Here, psi is the total molecular wave function. Little r with the double underline represents all the electronic degrees of freedom in the system, and capital R, all the nuclear degrees of freedom, and T stands for time. H is the total Hamiltonian of the system and contains several terms. The first 2 terms are just the molecular Hamiltonian. The first one we call Born-Oppenheimer Hamiltonian, and it contains the electronic kinetic energy, electron-electron repulsion, electronuclear attraction, and nuclear-nuclear repulsion terms. The second term is just the nuclear kinetic energy operator. And then we could have relativistic corrections, for example, to account for spin-orbit coupling and external perturbations such as the interaction with the laser field. But for the remaining of this talk, we're going to neglect spin degrees of freedom, and we are going to consider the field-free dynamics right after photoexcitation. So we don't include explicitly the pulse in the simulations, we just simulate what happens right after the field is turned off. The total molecular wave function can be expanded on this basis, which are the eigenstates of the Born-Oppenheimer Hamiltonian, obtained at every internuclear geometry. So at every possible internuclear geometry, we solve the static eigenvalue problem for the electrons, and the set of energies we get as a function of big R are the potential, adiabatic potential energy surfaces of the system. The lowest value one is the ground state, and then we have excited state. And these nuclear coordinate dependent coefficients in the expansion are wave packet components associated to the different electronic states. And if we plug these ansatz into the time-dependent Rödinger equation, we get a set of coupled evolution equations for the different wave packet components that are able to exchange population through these non-adiabatic coupling terms. So these non-adiabatic couplings essentially induce electronic transitions via the nuclear motion. And normally this term involving second-order derivative with respect to the nuclear positions nu are neglected versus the non-adiabatic coupling vector. In the Born-Oppenheimer approximation, these terms are set to 0, the non-adiabatic couplings, and that means that the motion of the electrons is uncoupled from that of the nuclei. And by that I mean that the nuclear motion won't induce electronic transitions. So a wave packet starting on a single state will remain in that state throughout the dynamics and move adiabatically on that surface. That implies that we're just keeping one term in the expansion here. So the Born-Oppenheimer approximation has been tremendously useful describing molecular dynamics at room temperature, as the typical thermal energies are much smaller than the energy required to excite an electronic state. However, this failed tremendously when we go to photochemical dynamics. And then we might ask ourselves, is there any way to keep just one term in the product in an exact way? In other words, is there any exactification of Born-Oppenheimer? And if there is, will that reduce to Born-Oppenheimer in the adiabatic limit? And the answer is yes. The answer is provided via the exact factorization approach. So in exact factorization, the total molecular wave function can be exactly written as a single correlated product of a marginal term that we're going to see shortly can be interpreted as a nuclear wave function, and a conditional term that parametrically depends on the nuclear coordinates that can be interpreted as a time-dependent conditional electronic wave function. Now, this factorization can be shown to be unique up to a phase, provided this partial normalization condition. And this just simply means that I can always multiply chi by a phase and phi by the opposite phase and get the same product back. I said that chi can be interpreted as a nuclear wave function because from it we can get key nuclear observables. For example, we can get the density as it will be obtained from the full molecular wave function. We can get the current density from the modulus and phase, and then we have a term here, a vector potential arising because of the coupling with the electronic subsystem, and we're going to comment on this term in just a few seconds. And we can also get the nuclear momentum. The nuclear momentum is the expectation value of this operator over the full molecular wave function. We can obtain it as the expectation value over the nuclear wave function with a vector potential term arising again. And if we take a closer look at this term, just written explicitly this polar representation, we can see here that the first two terms are related to this current density, so they are essentially a nuclear momentum field. But the third term that appears as a purely imaginary correction is the so-called quantum momentum. And we are going to see that this quantity is quite central in trajectory-based methods developed from the exact factorization approach. Note also that since the momentum must be real, then that term should integrate to zero. And that can be seen as an exact condition for developing approximate methods. So now, how do the evolution equation for those two probability amplitudes look like? Well, they look like this. And I just want to first want you to point out that the terms that I'm highlighting in red contain the exact electronuclear correlation. Let's first take a look at the evolution equation for chi. We can see it has a Schrodinger-like form in the presence of a scalar and vector potential, whose expressions I'm showing here, and they actually depend on phi. So the evolution equation for chi depends on phi through these exact potentials. And likewise, if we look at the time evolution equation for phi, this electronuclear coupling operator appears, which depends on chi. So we can see how these two evolution equations are intimately correlated, and in fact they should be solved side by side. And I just say that this is a scalar and vector potential, and in fact, under the phase transformation that I saw before, these transform just as standard potentials in electrodynamics. So in a sense, this evolution equation can be thought of as being driven for an effective electromagnetic field generated by the wave function of the electronic subsystem. So now I just want to compare side by side the Born 1 versus the exact factorization picture using a hypothetical two-level system. Now remember, both pictures are exact, just different ways of looking at the same process. And in the Born 1 picture, we have a ground and an excited state, and a nuclear wave packet starting on the first excited state. Now as the dynamics proceed, this wave packet will slide down and encounters this nonadiabatic coupling region where it can transfer population and essentially split the density. Now if we look at the same process through exact factorization lenses, I'm just keeping the adiabatic states for reference, but we have a single time-dependent nuclear wave function that evolves in a single but time-dependent potential energy surface that will develop some features such that it can split the nuclear density. So, okay, so far we've talked about how to treat or solve the TDLC in an exact way, but even though this equation looks quite simple, in fact it is not, and analytical solutions exist only for hydrogen-like atoms, and a full quantum mechanical treatment is limited to a few degrees of freedom. Now there are methods like MCTDH with better scaling properties, but they are still limited to few atoms, and they require pre-computed potentials. Now, mixed quantum classical methods offer a good alternative because they have a good trade-off between accuracy and efficiency. So the idea is that we want to treat the slow-moving degrees of freedom, the nuclei, as classical-like particles, that's F equal ma, and the electrons will be treated quantum mechanically, with some feedback algorithm between classical and quantum subsystem to recover nonadiabatic effects. So essentially, we are replacing the time-dependent probability density by an ensemble of classical-like trajectories. Each of them is going to have a set of associated evolving electronic coefficients. Now, the two traditional mixed quantum classical approaches are NFS dynamics and surface hopping. I'm going to comment on this in a little bit. But there's a big variety of methods that have been developed over the years. For example, we have path integral-based methods, such as ring polymer surface hopping, or nonadiabatic ring polymer molecular dynamics. Now these methods have been quite successful in describing nuclear quantum effects. We have Gaussian-based methods, for example, ab initio multiple spawning, methods based on the mixed quantum classical Wheel equation, methods based on the factorization, to which I'm going to devote quite a lot of time today, spin mapping approaches, or semi-classical methods. But for the remaining of this talk, I'm just going to focus on traditional and exact factorization-based methods. So let's first take a look at these two. In these two methods, the time evolution equation for the quantum electrons is obtained from this time-dependent self-consistent field approximation. So in TDSEF, the total molecular wave function is approximately expressed as an uncorrelated product of a time-dependent electronic wave function and a time-dependent nuclear wave function. Note here that phi doesn't have a parametric R dependence, such as in the exact factorization approach. And then you just solve this equation on the position of the classical trajectories, and you get a time evolution equation for the electrons, which can be also expressed in an adiabatic basis as an evolution equation for the electronic coefficients. So we know how the electrons are evolved. How about the nuclear force? In Ehrenfest, the trajectory propagates on a mean field surface, so the force is just given by the gradient of the expectation value of the Born-Oppenheimer Hamiltonian over the instantaneous time-dependent electronic wave function. So just the nuclei propagates on a mean field surface. This method is actually just derived by taking the classical limit from TDSEF. It does not require a basis expansion, meaning that you can directly propagate this equation, for example, with real-time TDFT. It's consistent but overcoherent, meaning that the system remains overly coherent when it should decohere. It doesn't predict wave packet splitting, as you can imagine, due to the propagation on a mean field surface. And energy is conserved for each trajectory. And we're going to see later that that's not really justified. So in order to fix the problem of wave packet splitting, surface hopping was developed. So in surface hopping, its trajectory is going to propagate on an adiabatic surface, and the trajectory can make stochastic hops between the surfaces based on a certain probability that depends on the non-adiabatic coupling vectors and the velocity of the trajectory. And in the hope that running many trajectories, because of these stochastic hops, we recover wave packet splitting. Now this method requires a basis expansion because we are solving these equations in a given basis. It's inconsistent and overcoherent because there is a disconnect between what the trajectory is feeding and the electrons. The trajectory is just propagating on a single surface corresponding to a given electronic state, but from the electron point of view, the propagation is in a coherent superposition. Surface hopping predicts wave packet splitting, and it also enforces that the trajectory-wise energy is conserved just by every time the trajectory hops. This is enforced by rescaling the velocity appropriately. So then what's the right force driving the nuclear particles? Should it be mean field? Should it be adiabatic? Should it be none of them, perhaps? So to these questions, what's the correct force driving the nuclear motion? And how can we treat this consistently with the electronic equation? The exact factorization will provide an answer. Remember that the nuclear evolution is a Schrodinger-like equation with a scalar and vector potentials. So therefore, we can point to a uniquely determined Lorentz-type force that should be driving the nuclei. Here, E is an effective electric field, which is related to the vector and scalar potentials. B is an effective magnetic field. And F is an internuclear force term that arises because of the coupling with the electronic subsystem. So again, the time evolution for the nuclei can be thought of as being driven by these fictitious effective fields generated by the electrons. So in this framework, there has been different mixed quantum classical methods developed. The first one ever derived was CTMQC, the coupled trajectory mixed quantum classical method. And I just want to compare side by side how CTMQC is derived from exact factorization to how Ehrenfest is derived from the TDSEF. First note that here we have a parametric dependence on R, and this is exact. This is an uncorrelated product instead. So we take the classical limit for the nuclear motion. We expand the electronic equation in a basis, in a adiabatic basis, and note again that this parametric dependence is inherited by the electronic coefficients, whereas here the coefficients just depend on time. And this we will see is going to be key to capture spatially resolved properties. And then on CTMQC, because we have these extra terms arising from this parametric dependence on R, we have to make certain approximations to make a practical method based on exact studies and numerical convenience. So we do that, and we get a set of equations for the time evolution of electronic coefficient in state L, and for the force of the nth nucleus. And I just want to say that for CTMQC, we essentially get Ehrenfest plus corrections. And these corrections are going to couple our trajectories, as we're going to see now. So let's take a look at how these terms look like. So this is how these corrections look like, and I'm going to go walk you through the different terms. We have a Q here, which is the nuclear quantum momentum that I introduced at the beginning of the talk. And this term is going to induce non-local effects because of the dependence on this gradient of the density. F is the accumulated Born-Oppenheimer force, and this is simply the time-integrated adiabatic gradient with a minus sign. And the C's are the electronic coefficients for state K, and delta F means FL minus FK, delta FLK. CTMQC has successfully been applied to many different systems, capturing the coherence from first principles, among other things. These are just few examples. And I just want to point out that we have, with this term here, a new mechanism for electronic transition, which is not present in traditional approaches. And note that this term couples all electronic states through this K-sum over electronic states and these products. And this is going to have tremendous consequences. For example, in capturing the pairwise nature of electronic coherences and in describing multi-state interactions. And we're going to see two examples of this in a little bit. So, okay, we have this quantum momentum, but how do we actually compute it? Because as far as I know, we have an ensemble of trajectories, not a density in the first place. So how do we do that? In the original CTMQC algorithm, this was computed by just representing the density as a sum of Gaussian functions centered at the position of the trajectories, and just applying this analytical definition, and that's what we call the original definition of the quantum momentum. Now, there's a problem with this way of doing things, which is that it can cause spurious population transfer. And by that I mean that if we compute the trajectory average population transfer to a state L, we get these two terms. So actually here rho LK just means CL star times CK. And what we see here is that even in regions where the nonadiabatic couplings are zero, we can still have population transfer induced by that term. So that means that away from regions of electronuclear coupling, we still can have population transfer, which is not physical. And in order to fix this, it was proposed that the quantum momentum can be redefined such that we enforce that the trajectory average contribution of this term is 0. And that's what we call the modified definition of the quantum momentum. And I just want to stress that each trajectory individually can still have quantum momentum induced transfer. It is just the average term that is 0. So this will compensate to yield a 0 net contribution. And this property actually is key for recovering spatially resolved electronic observables. One example of this is this system we studied. So we have a ground state and an excited state, and we start in a coherent superposition of these two states with a 0 momentum. And as time goes by, the excited state wave packet will slide down and move away from the trapped ground state wave packet and decohere and approach this nonadiabatic coupling region. But I just want to focus on what's happening on the first step, even before this reaches the nonadiabatic coupling region. Since we're away from the initial region, there shouldn't be any transfer of population. And let's look at the spatially resolved electronic populations on the excited state at different time snapshots. Here the green dots represent Ehrenfest trajectories. So what we see is that at times proceed, the Ehrenfest populations do not change for each trajectory. They remain without changing. Instead, in CTMQC, we see that there is a spatial structure being developed, and it tracks quite nicely the exact quantum dynamics results shown in black. And the trajectory average contribution is not changing. It is just the term is developing a spatial structure in the coefficients. And as you can imagine, this is going to be key if we later encounter an adiabatic coupling region for getting the subsequent non-adiabatic dynamics. So the trajectory average populations do not change, but CTMQC recovers this spatial structure. So in a sense, the Ehrenfest trajectory averages are hiding the wrong spatial structure, because if we just look at trajectory average properties, we don't see the underlying spatial behavior. Now, CTMQC is a coupled trajectory method, and can we make computationally cheaper methods? So there's been exact factorization-based surface hopping algorithms developed. The idea behind this is just to stick the time evolution for CTMQC within a surface hopping framework for the nuclei. And essentially we are replacing the nuclear propagation on this approximately TDPS by a purely adiabatic propagation where the surface hops are kind of mimicking the steps that the TDPS develops in coupling regions. So we have a coupled trajectory surface hopping method that essentially is the electronic evolution of CTMQC with coupled trajectories within a surface hopping framework for the nuclei. And then we have an independent trajectory scheme called SHXF. We run purely independent trajectories, and we use these auxiliary trajectories that are launched on non-active states that become populated and put a little Gaussian there to locally approximate this density and the quantum momentum. And the advantage of this, of course, is that we can fully parallelize the dynamics. And here I'm just showing the comparison of the two algorithms, CTMQC and SHXF. And I just want to note that here all the steps are parallel, but this quantum momentum step that I'm representing as a node and a fork, because it has to be done serially. However, in SHXF, since all are independent trajectories, every step is parallelizable. So we reduce the computational complexity from n trajectories squared to n trajectories. So that's quite nice. And now that we've set the stage, I just want to transition to the scientific contributions of this thesis. And in particular, and for the sake of time, I'm going to discuss two main areas: energy conservation in coupled trajectory methods, which is going to be key for stability and accuracy of the non-adiabatic dynamical simulation, and the description of electronic coherences in molecules. So let's begin with energy conservation. Energy conservation, as we all know, is one of the most fundamental laws of nature. And in a closed molecular system, energy exchange can occur between the translational, rotational, vibrational, and electronic modes, but in such a way that the total energy of the system, as given by the expectation value of the Hamiltonian over the full molecular wave function, should be a constant of motion. So energy shouldn't change in a closed system. In a mixed quantum classical description, the classical energy has two terms. First one is the classical kinetic energy for the nuclei, or the trajectories. The second one is the potential given by the electrons. What we should find, if energy is truly conserved, is that the time derivative of the energy should be zero. So let's first look at how the traditional methods do. Ehrenfest dynamics, since the force is purely conservative, it's just the gradient of the potential, energy is conserved for each trajectory. Now in surface hopping, energy will be also conserved, as this is just the gradient of the potential. And if the trajectory hops, as I mentioned, we enforce it to be conserved per trajectory by just rescaling the velocity. So LFS and surface hopping, each individual trajectory conserves the total energy. However, this is not really justified. It should be the ensemble energy that represents this underlying probability density that must be conserved. So this is kind of hinting us that we need coupled trajectories, because in principle, nearby trajectories should be able to exchange energy. So we have a coupled trajectory method. Let's see how it does in terms of energy conservation. If we evaluate the time derivative of the energy, though, we will find that this is not zero. So energy is not conserved. It is the presence of these quantum momentum terms in both force and electronic evolution that are breaking energy conservation. So how can we fix this? Well, remember that the quantum momentum was redefined to satisfy this no-spurious transfer condition just by solving this. And when we were playing with the maths of this equation, we actually recognized this term up here. So that means that if we could make this term here trajectory independent somehow and pull it out of the trajectory sum, it will be multiplying as zero and energy is conserved. So that was our whole idea. So we thought of, why don't we redefine the accumulated force such that every term in the trajectory sum equals the trajectory average contribution. If we solve for that equation, our new accumulated force satisfies this equation, where this Tn is just the nuclear kinetic energy for trajectory alpha, and that's simply our CTMQC E method. And I just want to say that the E stands for energy. I didn't name the method after myself. And so we study several examples and see how this CTMQC-E performs. The first one I'm going to show is the ultra-fast cis-trans isomerization of PSB3. And this PSB3 is a model of 11 cis retinal, which is a chromophore present in rhodopsin, a protein which is responsible for light vision in vertebrates. And this protein is located here in the retina of the eye. And when light comes through the eye, one of the key processes in the vision is that this molecule, 11 cis retinal, isomerizes to the trans photoproduct. So simply, this molecule gets excited to a first excited state, and then it goes to this crossing region, forming the trans photoproduct. And this whole process has been shown to be driven mainly by three modes, which are this bond length alternation, that's just the difference between singles and double bonds in the molecule, this torsion angle between these four carbons, and this hydrogen out of plane wagging. And PSB3 is a good model of 11 cis retinal because it's been shown to display a lot of the same features for the potential energy surfaces involved in this process, mainly the S0 ground state and the first singly excited state. So we studied this ultra-fast cis-trans isomerization of PSB3. We use a reduced dimensionality model that considers these three main modes that drive the isomerization of 11 cis retinal and also PSB3. And first, we computed the excited state populations and the energy deviation with exact quantum dynamics, as I'm showing here in black. surface hopping with energy decoherence correction, which is shown in green. This is just a decoherence correction to try to decohere. CTMQC is shown in blue, CTMQCE is shown in red. We can see that all methods predict this decay, at least qualitatively. Now, if we look at the energy, we can see that CTMQC actually gains quite a bit of energy on the process. Just to give you an idea on this scale, this is the excitation energy at the Frank Condon point for this molecule. And we can see that this is greatly reduced with the energy correction of CTMQCE. Now, if we look at some nuclear observables, we computed the expectation value of the nuclear momentum along this BLA coordinate and its variance. And we see that all methods track the exact quantum dynamics. However, if we look at the spread of the distribution, we will observe that CTMQC actually start deviating a lot from the mean value, having these extreme values for the distribution. Essentially, some trajectories are just gaining a lot of energy along those modes. And CTMQCE in red fixes this again. And to get an idea of what's happening, actually, we look at some selected trajectories. Here I'm showing the value of the BLA coordinate and the momentum along BLA. What we see is as the dynamics goes by and the system starts getting energy, this momentum starts, this started gaining a lot of momentum, and this makes that the R coordinate, this BLA, start oscillating with high amplitudes. So this is fixed with CTMQC, dampening these oscillations, and as we can see, this algorithm greatly improves energy conservation and yields better nuclear observables. Second example we study is the ultra-fast photorelaxation dynamics of the uracil radical cation. And these radical cations are generated during the photoradiation damage of DNA with UV light. They are involved in oxidation processes within the body and charge transfer of DNA. So it is quite important that we understand how these nucleic acid components of the DNA behave under certain environmental conditions. And we're going to study this uracil radical cation. This system gets excited and ionized, and it's been shown that before fragmentation, it relaxes through a 3-state and a 2-state conical intersections. So to study this process, let's first start how CTMQC does, just plain CTMQC. And we use a linear vibronic coupling model that was developed in this reference to actually match the photoelectron spectra as obtained from the experiment with MCTH. So I forgot to say there are 4 electronic states involved in this process. And first here I'm showing what's going to be our reference, which are MCTH calculations. And we see that in this region actually there is a simultaneous decay of the D2 state and simultaneous rise of D1 and D0, and that means that we are just hitting this 3-state conical intersection between these states. First, we computed the population with surface hopping with energy decoherence correction, and actually we see that very early the population starts deviating quite a lot from the exact reference and soldering off, as we can see here. Ehrenfest does kind of the same thing. It just deviates a lot in this region, and the subsequent dynamics is also far away from the exact reference. But CTMQC, however, tracks quite nicely the reference MCTH, especially during this 3-state conical intersection region. So, unlike traditional methods, CTMQC is capturing this dynamic through a 3-state conical intersection. And as I said at the beginning, something key for this to happen is the shape of this term, which couples all electronic coefficients. So this is key to capture dynamics when we have more than 2 electronic states involved in the process. We need a term such like this that couples all electronic states. How about the energy? I just showed the populations. And first we computed some nuclear observables such as this average bond length during the dynamics. This is the same color scheme as before. Black is exact, blue CTMQC, red CTMQCE, and SHEDC in green. So what we see here, for instance, if we look at this particular OH bond length, is that, so that CTMQC starts actually, as time goes by, deviating a lot from the exact reference. And this is greatly improved with CTMQCE. And this is something seen across the different bond lengths. CTMQCE gives an improved bond length during the dynamics. Now, we look at the energy, we see that CTMQC is gaining a lot of energy during this process. For this system, is quite a lot, and we can reduce it almost by half with CTMQCE, although we have still some residual energy. Now, CTMQC, as you remember, does pretty nicely in terms of populations, and what we find here is with CTMQCE, the populations are worse. These are the dots right here. They are still better than surface hopping, but not as good as CTMQC. So for this particular case, CTMQC is given worse electronic observables, and that's mainly because we are redefining the accumulated force, so it's losing in a sense it's losing their first principles interpretation or derivation. Now, I'm just gonna go through the last topic, which is the description of electronic coherences in molecules. So, the first thing is, what are electronic coherences? We define the spatially resolved electronic coherences between these two states, as the complex product of the two nuclear wave packets associated to two particular electronic states. Now, this is something I think I haven't said before, but remember that the full molecular wave function can be represented exactly either in bond-one basis or in the exact factorization basis. So that means that we can relate these two if we expand phi in the same adiabatic expansion. And that just means that the wave packets will, in state k, let's say, is just simply the electronic coefficient in state k times the wave function. So then we can express this in terms of the C's through the density. Now, the spatially integrated electronic coherences, that's what people tend to refer to coherences. It's just the overlap between the two wave packets. So it measures the overlap in nuclear space. And in the case of using trajectories, we can represent the density as a sum of delta functions. So this is just simply the trajectory average contribution of this product of electronic coefficients. So why do we care so much about electronic coherences? Electronic coherences can be used as control in photoinduced chemical transformations. So let's look at this particular example. We have a ground state wave packet, and through a multiphoton absorption, we create a coherent superposition of these two electronic states. Now, as the surfaces are parallel enough, these two will move together and remain coherent. So if we recouple the states, for example, with a second probe pulse, we can use the interference patterns between these two wave packets to tune the yields or the photo products. They are used also to probe these electronuclear dynamics and get a picture resolved in electronics and nuclei areas. And actually, to have this control, we need long-lasting electronic coherences, and these have been experimentally measured in the laboratory. And also now, they can be measured with spatial resolution. So the experimental group has developed several techniques to measure actually these spatially resolved coherences with sub-Armstrong resolution at some femtosecond. So this is quite nice. Usually, on the nonadiabatic community, we tend to focus a lot on decoherence, but how about coherences and recoherences? These are very important as well. For example, in this paper, they measure the charge migration in silane, this molecule. It's a purely electronic-driven process, and they saw that this charge migration decoheres within 15 femtoseconds, but then recoheres after 50 femtoseconds. So this coherent recoherence is driving this charge migration in this molecule. So what are the challenges for simulations? The first one is that electronic coherence is a state pairwise property, so it depends on two electronic states, but the usual ad hoc decoherence corrections for traditional methods are state-wise. And I'm showing here two popular decoherence corrections. I just want you to focus on the terms that I'm showing in red, that basically the correction for state L depends only on the state L itself and an active state. So we're going to see shortly that this is actually a problem for capturing the true nature of coherences. We might, excuse me, we might ask ourselves, are quantum aspects of the nuclear motion significant? Or we can capture the right physics with a classical-like picture for the nuclei. And if an experiment measures only the spatially integrated, we don't have imagined spatial resolution, does this spatially resolved character matter at all? Or perhaps not? So let's first look at the first point here, pairwise nature of electronic coherences. And to study this, we use this very simple model system that was developed in Levine's group. So we have two parallel states and a third non-parallel one. All the couplings are set to 0, so the states are not coupled. And we start in a coherent superposition of these three electronic states. Now what we should find is that the dynamics goes by, the two wave packets on the parallel states should remain coherent, but simultaneously decohere with the third state. So we computed this, the magnitude of the electronic coherences between the parallel states, and I'm showing this here. Exact results are shown in black, and we computed also Ehrenfest, SHCDC, CTMQC, and two surface hopping methods based on the exact factorization. What we see here is that SHCDC dumps exponentially this coherence between the parallel states, which is not right, whereas the rest of the methods actually predict parallel coherences. Now, if we look at the coherence magnitude between the non-parallel states, what we see is that SHCDC in orange, again, dumps exponentially these coherences. Ehrenfest on the other extreme, shown in green, predicts that these are constant between the non-parallel states. CTMQC shown in blue and coupled trajectory surface hopping in red predicts this decay, perhaps a bit slower than it should, and with some residual coherence, and the same goes for SHXF, which is an independent method based on the exact factorization. So we see that the exact factorization-based method gets this pairwise nature of coherences, while traditional SHCDC decays all coherences, Ehrenfest on the other extreme, everything remains constant. So just looking at this, we might think maybe Ehrenfest is good to predict coherences between parallel states. Is that right? Well, how about the spatial resolution? So then we look at the spatial resolution of these coherences, and I'm showing just here two particular time snapshots in the dynamics. Black are exact results, Ehrenfest trajectories are in green, CTMQC in blue. So if we look at this time step, actually, what we see is that Ehrenfest, for each trajectory, the coherence between the parallel states, the magnitude is not changing at all, while CTMQC again is developing a spatial structure that tracks the exact quite nicely. Again, the spatially resolved property is not changing. Sorry, I'm pointing to the wrong graph. Spatially resolved property is not changing, but the spatially resolved level, CTMQC actually gets this spatial structure right. So trajectory average might hide the wrong spatial structure. What are the consequences of this? Well, first, this spatial resolution now can be measured in an experiment. And second, as you can imagine, for subsequent dynamics, for example, if we have a later nonadiabatic coupling region, if we don't get right what every trajectory should do, it's going to be hard to get the subsequent dynamics. So to prove this, we came up with this L20 SAC model, which is basically this model right here, but then we stick a single avoided crossing between the parallel states at a later time, center at -20. Yes, let's set it at 0, I'm sorry. And let's look at what these methods do here. And here I'm showing the populations on the excited state and the same coherence and magnitudes, but I just want to focus on this region. That's the populations when we enter this nonadiabatic coupling region. What we see here is actually CTMQC predicts at least qualitatively the population transfer to this state, and Ehrenfest actually does something completely wrong, which is reversing the side of the population transfer. And this is because, as I said later, we look at the spatial resolution at the time snapshots. Ehrenfest is not changing until it encounters the nonadiabatic coupling regions because of this lack of quantum momentum induced transitions, where CTMQC actually tracks the quantum dynamics, and it tries to do that on the coupling region. So in RFS, the wrong spatially resolved coherences lead to the wrong subsequent dynamics. So even if the trajectory average population or coherences might agree, spatial resolution is key for the subsequent dynamics. So how about recoherences? How does CTMQC do for recoherences? We came up with this very simple model system. Again, we have two parallel parabolas and a third non-parallel one, and we launch a coherent superposition of these three uncoupled states. So what we're going to find here is a first decoherent event, but as the wave packet on this surface reflect back, we are going to so we find recoherence. So first decoherence and then recoherence. So we computed these electronic observables. First, let's look at the populations of one of these parallel states. I said nonadiabatic couplings are 0, so we shouldn't find any population transfer. But SHEDC, shown in red, and SHXF, shown in purple, shows spurious population transfer when they shouldn't. Now let's look for now at the top plot, coherence magnitude between the parallel states. We see that Ehrenfest predicts constant coherences as it should, CTMQC the same, SHEDC and SHXF again dumps this coherence when they shouldn't. So SHEDC and SHXF are showing population transfer, spurious population transfer and coherence. Now if you look at the coherences between the non-parallel states, as we saw before, Ehrenfest just predicts they should be constant, and the rest of the methods actually show the decay in this coherence between the non-parallel states. So again, these two show the spurious transfer and dump when they shouldn't. Ehrenfest doesn't dump anything at all. And CTMQC and CTTSH are, well, not CTTSH, I'm not showing it here. CTMQC is capturing the right behavior, but as you probably notice, what's this peak here, right? None of the methods is capturing this recoherence peak. So all methods are missing the recoherence at 32 femtoseconds. Why is that? What's missing in all these methods? And to see what's happening, we went to an exact, we developed an exact trajectory-based picture, just simply from the time evolution of the electronic coherences, and using the exact factorization approach to develop this trajectory-based picture. And ultimately, we replace the density by a sum of delta functions to study what the trajectories are doing. And if we massage the math a little bit, we're going to get that in regions of zero nonadiabatic couplings, the time evolution of the coherence magnitude for each trajectory should have this form. And it looks quite complicated, but we have new terms appearing here. This Q, which is the projected quantum momentum, as the gradient of the magnitude of the wave packet, over the wave packet. And we have this term that is the reduced quantum momentum, which is the gradient of the magnitude of the electronic coefficient over the electronic coefficient. So actually, in CTMQC, these terms are set to 0, because in approximation, in the derivation is approximated that theirs are 0, and that essentially means that the projected quantum momentum is being approximated by the nuclear quantum momentum for every nucleus nu and electronic state k. So actually, if I compare the exact with CTMQC, we have these extra terms appearing here. And actually, after the system decoheres, this term tends to 0. And only these terms survive to drive the coherence. Even though they are multiplying at 0, but note that these have C magnitude in the denominator, so they will cancel a contribution there. So these terms actually are the ones driving the coherence. And here we computed the exact values of the quantum momentum shown in black for the 4 different type knot swaps during recoherence. In blue I'm showing the projected quantum momentum and the reduced contribution in red. And what we are seeing is that in these regions where the wave packet recohere, this reduced contribution is actually non-negligible. It's in red, I'm showing here. And you also can see that this contribution is kind of crunching down the projected quantum momentum, to yield a projected quantum momentum, which is kind of a straight line. So this recoherence is actually driven by this that we call crunch. And finally, I want to provide some conclusions and outlook. So as conclusions, exact factorization offers quite valuable insights into the interaction of a couple quantum subsystems. It's a rigorous starting point for developing mixed quantum classical schemes. And these quantum momentum driven effects that appear in those methods are key to capture effects which traditional methods cannot. For example, decoherence, multi-state dynamics, long-lived electronic coherences, and spatially resolved properties. And these exact factorization-based methods have already been very successful, but they are 10 years old, so there's definitely room for improvement. And as future research avenues, we could think of designing improved couple trajectories algorithms, for example, imposing more exact constraints to calculate some coupling terms, reinstating some terms, for example, this nonadiabatic crunch that I talked about before, or perhaps deriving new methods. We could also think of dynamical bundles approximations, where we couple and decouple the trajectories on bundles during the dynamics. We could also think of improving CTSH so that all the things that it inherits from surface hopping are computed over the whole ensemble of trajectories, for example, hopping probabilities and energy conservation. And ultimately, we would maybe want to have representation-free methods where we don't rely on a basis expansion. That's going to be quite useful to treat extended system with many electronic states. And test CTMQC in more applications, for example, describing non-linear electronic coherences in molecules instead of a model system. And these have been experimentally measured in this thiophene molecule, and we are already doing the first tests to see how CTMQC does describing this system. And I just want to thank the committee members for being here today, all my amazing group at Rutgers, my collaborators on my scientific publications, everyone for being here today, funding agencies that funded me through my research, and the codes I've used during my work. And I just want to finish this presentation with some pictures over the years that I've really enjoyed my time here. And with that, I want to conclude, and it is time for